We talk about now the vestigial sideband modulation, which is a compromise between the single sideband modulation and the double sideband modulation. And what we'll see here is that one sideband is almost completely passed, and the word almost here is means exactly that one band is passed completely, whereas a small portion of the other sideband, or a trace, uh, or a trace of the other one, of the other sideband, is also is retained, so that when we are transmitting, it is like you are transmitting 1.25 or thereabout of what you are transmitting with the single sideband. So if we just look at the diagram that illustrates the single sideband, is that you have the spectrum of the message as illustrated here. Therefore, when it is modulated, the spectrum is shifted and it becomes centered at omega c, the omega c being the center frequency of the carrier. And therefore, when we now want to get either the upper sideband or the lower sideband, like we did with the single sideband modulation, we would require to have a filter that will just cut off a portion of that, so that we can either cut off this one or you can cut off the other one. But now for this, we are going to be getting the filter that takes a form like this one, such that it is sure to get, and that is actually where we mean almost, because we are not getting the full spectrum of this of either of the sideband. It is, we are cutting half of it on one side, and then the other side is fetched from the other sideband, and therefore, like you can see, there is a portion that has been cut out from that side, and this portion is reciprocated by getting another portion on the lower sideband. So at the end of the day, we end up with a spectrum that is 1.25 or 1.2 or thereabout of SSB modulation scheme. So there's some advantage to this, and we'll see shortly. But clearly, that is how that is how we end up with a vestige or vestige, and we call vestigial. We call this type of modulation vestigial sideband modulation. So we generate the vestigial sideband signals as follows. The first thing is that we follow the same idea like we have done before to generate the double sideband modulation. Therefore, after we multiply the message signal with the carrier frequency, or this is what we achieve by the initial modulation, or the double sideband modulation. The only thing we can observe here is that we have higher amplitude than we have done before, but we will see the effect of that shortly. Therefore, the output of our modulation is the double sideband modulated signal. But then before we transmit it, we have to pass it through a vestigial sideband filter. The filter is the one that we have just seen here, that will cut a portion of one sideband and a very small portion of the other sideband. Therefore, we end up with the spectrum that we have just seen here. The modulation of the vSB signals involves or may be accomplished by synchronous or coherent demodulation, just like we did with the DSB. And you can see figure 311 that is illustrated here. In this case, we are receiving the vestigial sideband signal at this point, where you multiply with the local carrier having the frequency omega c. Then you get the demodulated signal dt that has two that has a term that has double frequency component. If you remember what we did, is that x vSB, a function of t, we look something like m of t cos omega c of t, if we assume that it takes the portion that the full portion just like DSB. And now if you multiply this with cos omega, which is the carrier, cos omega ct, carrier we normally separate it as we separate it with x of t, and x of t was equivalent to cos omega c of t. You just follow the same thing, you're going to find that we end up with a half of m of t that has a 1 plus and a double frequency component that we were able to see something like this. And therefore, we are able to remove this term using the low pass filter. And this shows that if the frequency response h of omega will have anti-symmetry about the carrier, as shown in figure 312. Before we, of course, come here, we need to rectify something and say that there is a condition that we have set, which is required if we are to fully recover the vSB signal that has been filtered by the vSB filter. So we are saying that this would, of course, work if we are working with the DSB. But now we are saying that before we, for us to work with vSB, we are passing it through a filter that is cutting off a portion of the upper side band and a portion of the lower side band. Of course, the bigger portion of the upper side band and a very small portion of the lower side band. And the characteristic of this vSB filter must be known and must meet some condition so that our message signal MT is fully recovered at the demodulator. And we are saying that we can use the synchronous or coherent demodulation. And therefore, this requirement can be shown that for a distortionless recovery of MT, there is a condition that has been stated in figure 311, problem 311, that says that the filter, this filter here, the vSB filter, must have the frequency response h of omega such that the condition 312 must be met, that h of omega plus omega c, that is a frequency shifted version of the frequency response itself of the filter, plus h of omega minus omega c must always give you a constant k for omega magnitude being less than or equals to omega m, this being the highest frequency component of your message signal m of t. So we are saying that there's a condition. So if this be the condition, therefore, if we set the constant, the one you're saying this constant, if we set it at 2 h of omega c, or if we say that this constant is equals to the cutoff frequency or the frequency response of our filter at the cutoff frequency, then that is still a constant that we can choose. If we set that to be the case, therefore, we can end up with this equation being expressed as this one. And I have just brought in just how we are achieving equation 3, 1, 3 from 3, 1, 2, that you have set that the equation 3, 1, 2, which is on the left, is equal to a constant on the right. So if you say that means be the case, if you bring one of these h of omega c on the left, becomes a minus, and therefore the equation left on the left is satisfied. Then if you take if this remains and you take the h of omega plus omega c on the right, it becomes negative. But then of course this will be plus. This is equivalent of saying negative times negative becomes plus. So this is how we obtain equation 313 simply by that simple manipulation of the equation 312 after equating it with this term. And it is equation 313 that actually shows that the system of frequency response of our vestigial filter has anti-symmetry, or it's unsymmetric about the carrier frequency. And this equation 313 clearly shows that. And the anti-symmetry is clearly visible in figure 312, whereby if you look at figure 312a, our equation 313, the one term illustrates the filter as indicated by 312a, and the other form is if you look at the omega c, you are either cutting the upper side band or you are cutting the lower side band. So one form of your filter allows you to cut off the lower side band, and the other term allows you to cut the upper side band. And that is how we are saying that it is an anti-symmetry about the carrier frequency omega c. And now figure 313 illustrates how we can perform the demodulation of the vSB signal after we have transmitted it, having cut off a portion of the signal, as we can see here, a portion of the sideband. You can see this message was meant to have been, the upper sideband should have been that full, and therefore it is shifted in frequency by the carrier, and therefore it is centered at the carrier frequency omega c. Therefore, if we have received now this message signal that is vestigial sideband modulated, so the first thing that we will do is to translate this frequency as we have mentioned, using the idea that I mentioned earlier, that you have x vSB signal, and you multiply it with the carrier frequency omega c of t, and when you do that, you end up with two terms. One is m of t centered at 0 frequency, then plus another one that is cos omega 2 omega c of t centered as at twice the carrier frequency. Therefore, you pass this signal through the low pass filter, which cuts it out, and therefore then your VSB, or rather the demodulator will, after passing through this signal, we are left with this portion of the message, and this portion of the message is simply treated such that it takes the initial spectrum of the message signal that was as indicated right here.